So chi-squared goodness of fit test, we have 3 conditions: random, 10%, and large count. Again, we're not going to do normal because it's not a normal distribution. It is right skew. You guys know how to check the random condition. It's just an SRS of whatever. The 10% is 10 times the sample size, has to be less than the population. So those two are the same. Now, large count. This is the one that's different. Large count condition. You need your expected counts to be greater than or equal to 5. You need your expected counts to be greater than or equal to 5. It is totally fine if when you go and take your data that you don't get anything in a particular category. It's fine if your observed counts are not greater than or equal to 5, but you need your expected counts to be greater than or equal to 5. So before we start, we have 2 important cautions. The first one is must use expected counts, not percentages. So you might be told that you should have a certain percent in each category, but you need to find out what the expected count would be for that particular category. So you do need to use the counts, the number of items in each category, not the percentage. The other thing is we must notate the expected counts in the problem. Now, we're usually going to do this when we check our large count condition. Okay, so this is usually under large count condition. That's generally where we put it. But if for some reason you have room in the table or something, that's fine. You can write it there. But most of the time we're going to write it here because we are verifying that the expected counts are greater than or equal to 5. So it makes sense to write them there. So that's generally where we're going to put them. But you can write them anywhere as long as they're somewhere in your problem. All right, so those are our conditions. And then obviously, you guys, we're going to still have our state plan do conclude. This is basically how you would do the state, would be this. We will test at alpha equals whatever, right? Depends on what the problem says, or use a 0.05 if nothing else. So we start out that way. Now, the null hypothesis is basically you're going to state something in the kind of realm of this particular statement. Obviously, you're going to use from the problem, the context of the problem. So the null hypothesis would be that the stated distribution of the categorical variable in the population of interest is correct. Now, that's all very fancy words to basically say that whatever they say it's supposed to be is what it is. And then the alternative is that it is not correct, that there's something wrong with it, okay? That what they're saying it should be is actually not what it ends up being. Then what you're going to do is you're going to find the expected count for each category, assuming that their distribution of claimed values is correct. So you're going to assume that to be the correct value. So once we get those, then we can calculate the chi-squared test statistic, which is basically the difference in the observed and the expected squared divided by the expected. Now, the good news, your calculator will do it for you. Yay! So here's how you're going to do this. You're going to put your expected, your observed counts are going to go into L1. Under stat edit, you're going to put your observed counts into L1. You're going to put your expected counts into L2. Your observed counts go into L1. Your expected counts go into L2. Then you're going to go to stat, test, and this one is D as in dog, and it says chi-squared GOF test, and that stands for chi-squared goodness of fit. It's going to ask you for your degrees of freedom. How do you find degrees of freedom? Yeah, so it is going to be our categories. So our categories -1. However many categories we have, -1. All right, so slight tweak, but same idea. However many categories we have, -1. So it's not the sample size, it's the number of categories -1, slightly different. And then we're going to find the p-value. The p-value is going to be the area to the right of the chi-squared value under the density curve with categories, so it's k-1 degrees of freedom. So we have a right skew distribution. We find out how far our data is from what we expect it to be. And whatever the area is to the right of that, it always goes to the right. That is your p-value. That would be your p-value. We'll compare that to the alpha level, and we'll make a decision. Cool? Cool. You ready to do it? Let's do it. Why not? Here we go. NHL players. In his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it at the highest levels of the game. Specifically, since January 1st is the cutoff date for youth leagues in Canada, where many National Hockey League players come from, players born in January will be competing against players that are up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it to the NHL or not, a random sample of 80 NHL players from a recent season was selected, and their birthdays were recorded. The one-way table below summarizes the data on birthdays for these 80 players. Do these data provide convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? All right, so if you look at this, this is the observed values. These are the observed values. This is what actually happened when we took our data. And so if we assume that the birthdays are evenly distributed, and we took a sample of 80, how many should we have expected to see in each of these 4 categories? Yeah, we should have expected 20 in each category. 80 people were selected. We should have expected 20 in each of these categories. Obviously, you can see that that did not happen, all right? So we're going to see if there is a statistically significant difference, or is it just a little bit of a difference? That's what we're going to test. So here we go. State. We will test at alpha equals, what are we going to have? Alpha B? 0.05. And our null hypothesis is going to be that NHL players birthdays are evenly distributed. That's what we're going to assume is true. However, we're testing to see if that is not true because we have a suspicion that it might not be true. So our alternative is that NHL players' birthdays are not evenly distributed. That's our null and our alternative hypothesis. All right, plan, random. We have an SRS of 80 NHL players. Our 10%. 10 times 80 is 800. We're going to assume that is less than the population of NHL players. So we have our random, we have our 10%. What's left? Very good. And I'm so glad that you said large count and not normal, because it's not normal. It is right skewed. So this would be large count condition. All right, for our large count condition, our expected counts, oops, I'm struggling to spell today. Our expected counts equal 20 per category, which is greater than or equal to 5. So we are good to go for our expected counts. Expected counts equals 20 per category, which is greater than or equal to 5. So everything is good. We are ready to do the do. Do you guys have any questions on the state or the plan for a chi-squared goodness of fit test? Super easy, right?
There's like 900 players in NHL.
Do what?
There's like 900 players, so it's close.
Yeah, this one was close because, yeah, there's about, I think it's like 9 something. Yeah, so good. All right, let's do. So for do, here's what we're going to do. We're going to use a chi-squared goodness of fit test. So we're going to use a chi-squared GOF test. So here's what you should do. You should go to stat edit. Stat edit. That's where your list is, L1 and L2. You're going to put your observed data, the ones that were in the chart, in L1. There's only 4 numbers, not that hard. Stat edit, put your observed values into L1. Then you're going to go over to L2, and what are you going to put into L2? 20, 20, 20, 20, the expected counts. So yeah, you're going to have 20, 20, 20, and 20. Put those expected counts into L2. 20, 20, 20, 20. Then you're going to, after you have your observed into L1, your expected into L2. You're going to go to stat test D as in dog. I'll give you guys a hint. If you go up, then it'll go to the bottom of the list and you'll be closer to the D. So if you go up, you'll be closer. Stat test D, chi-square goodness of fit test. It's asking you where's your observed. Hopefully you put in L1. Your expect is in L2. And then it's asking you for degrees of freedom. How many degrees of freedom? 3. Very good. So your degrees of freedom are 3. That was N, or categories minus 1. Sorry, categories minus 1. And then when you hit calculate or draw, you'll get the information. All right, so chi-squared. What is your chi-squared test statistic? 11.2. That means that our data was 11.2 standard units from being 20, 20, 20, and 20. Then it tells you your p-value. What was your p-value? 0.011. Okay, cool. Now, I do want you guys to see that underneath that it says CNTRB or whatever. That means contribution. That is in order, your categories in order. That is how much each category contributed to the chi-squared test statistic. Yes, ma'am? I would check my list then. If you got a whole different p-value, check your list and make sure that your list is correct. All right, so the contributions, that's how much each of the individual categories contribute to the chi-squared value. So you can see that first category contributes quite a bit. The second category contributes nothing. Why does it contribute nothing? Because the observed and the expected were exactly the same. The observed was 20, the expected was 20. So when we look at their difference, we get 0. When we square it, we get 0. And then when we divide by the expected, we still get 0. So our contribution for that second one was 0. All right. Conclude. Our p-value was 0.011. How does that relate to the alpha?
It's less than.
That is less than the alpha of 0.05. So what do we do when the p-value is low? Very good. We're going to reject the null hypothesis. Is there or is there not convincing evidence? There is convincing evidence. that NHL players' birthdays are not evenly distributed. And I can look at the data and I can look at the chi-squared contribution and I can see that it does seem like the suspicion of earlier birthdays contribute the most to the difference because the chi-squared contribution for that first category was really large. So it does look like that there's a big difference there. Is there a possibility we made a mistake?
Yes.
Yep. What kind of error might we have made? Type 1. So that doesn't change. The probability, or the fact that we have type 1, type 2 error doesn't change just because we're on chi-squared. We rejected the null hypothesis. We may have made a type 1 error. What's the probability we made a type 1 error? It's just the alpha value, which is 0.05. All right. So those things are still in play. So that's kind of good that you already know how to do that. What questions do you guys have about a chi-square goodness of fit test? Easy, right? Nice. All right, cool.